Hi, my name is Manish Gupta, and as part of this series on extreme classification, in this video, I'm going to talk about the DiSMEC, which is a distributed sparse machines algorithm for extreme classification. So let's get started. Earlier, label embedding and tree-based approaches were pretty popular for extreme classification. And let me sort of try to motivate what are the drawbacks of these kinds of methods, right? So as you might know by now, extreme classification is the problem where you essentially have, it's a multi-class classification problem, multi-label classification problem, where you have a very large label set and you want to choose for any given instance, a subset of this very large label set, a small subset of this large label set, okay? So typically extreme classification data sets show power law distribution of the labels. That is, a very large fraction of labels have very few positive instances, right? So essentially, for example, in these plots, you can see the same thing happening. So there are these plots for Amazon 670K dataset and Wikipedia 31K dataset. What is plotted on the x-axis is just the label ID. On the y-axis, you have number of training instances. So as you observe, for a very few label IDs and for very few labels, you have lots of labels, lots of training instances, while for many label IDs, you have less than 5 training instances, right? So this is log scale label IDs. So in fact, on Amazon 670K dataset, the highlighted portion essentially tells you that only 100K instances out of the 670K actually have greater than 5 training instances, right? Similarly, if you look at Wikipedia 31K, there are 31K total instances. But if I ask you, hey, how many of them actually have more than 5 training instances per label? Well, that would be somewhere around 5,000, somewhere around 5,000 out there. Okay. So that's that. So basically, there's a power law distribution. Now, label embedding approaches sort of assume that the label matrix has effectively low rank. And by the label matrix, I actually mean instances and the labels. So essentially, if you have instances and you have labels, that's the label matrix. And what you could do is to basically, I mean, this matrix is super sparse, right? This matrix is super sparse because most of the instances are not related to many labels. They're related to very few labels. Okay. So they assume that this label matrix is low rank, and therefore they actually try to express, these labels and also instances in a small embedding space. Now, those kinds of things are okay, but not okay for these tail cases. Several of these labels are essentially pretty tail. With power law distributed label space, unfortunately, therefore, this assumption of low rank breaks, which basically means that these global embedding based approaches sort of fail and they lead to high prediction error. Okay. So that is why label embedding methods are not really good for extreme classification. Similarly, tree-based approaches. In the previous video, I basically talked about several tree-based approaches like FastXML, like FastXML, and also other approaches. Right? However, the tree-based approaches are tree-based approaches are nice because they trade off prediction accuracy for log prediction speed, right? So log training speed and log prediction speed. However, the accuracy is not that great. In fact, they may fail if the decisions at the top are incorrect. Right? So those are the drawbacks of tree-based and label-based approaches. Now, what is DiSMEC? Well, DiSMEC is essentially distributed sparse machines for extreme multi-label classification. Okay, and we'll talk about what is distributed and what is sparse in this algorithm. Okay. DiSMEC is essentially a one versus all framework. So it basically says that, hey, for every label, I learn a specific classifier. In fact, the way I learn this classifier is to ensure that it gives higher similarity with respect to the class label to which the data point belongs to, and lower similarity to every other class label. Okay, so it's basically called as binary one versus rest framework for learning a weight vector WL corresponding to every label L. So for every label, you're going to learn a classifier, and this classifier is going to be preferring those particular instances which belong to the particular class, which belong to the class L. Okay. So, for example, for a particular class L, you're going to learn the classifier by optimizing optimizing this objective function. So you want to minimize and you want to find the WL, the weights which minimize this stuff. So what is this stuff? Well, this part is just L2 regularization. So you want to ensure that the vector that the classifier the separator, the hyperplane separator, is essentially as small weights as possible. So the complexity has to be controlled, and then this one sort of ensures that a particular WL that you train for this classifier should be very close to positive instances and far away from negative instances. This SLI basically takes care of the sign. So essentially, if the xi is actually belonging to the if the data instance xi belongs to the label L, a label class L, then essentially you have SLI, positive, else you have it negative. So basically, it controls for positive instances and negative instances, and then basically this loss function essentially just ensures that it learns a WL which has very high similarity with positive instances and very low similarity with negative instances. Okay. Now, the idea is that if you basically just use this framework and essentially train a label classifier for every label, now, for data sets which have like 325K labels, you can very easily end up with very large models up to 870 GB in size. Now, where do you store these models? It's pretty complex to basically store or work with these models. Even when you want to sort of, load these models or make inferences, it's very, very complex to do that. Okay. And that is where DiSMEC plays a role. So they essentially said that, hey, we're going to do two interesting things in this framework. First, we are going to do distributed training. So therefore, what they did was to essentially distribute the training across multiple machines. So at the top level, they essentially distribute the label set across several machines. And then within a particular machine, they essentially distributed the computation across several threads using OpenMP. So parallel processing in that sense. So they follow distributed parallel processing framework in that sense. Okay. The second thing that they did was to essentially train sparse classifiers. So they said that, hey, well, we will essentially do pruning. So what they observed is that although this particular model, 870 GB model, is so huge in size, about 99.5% of these weights are within this small threshold of minus 0.01 to 0.01 range. So this particular small range. Okay. Now, weights close to zero hardly have any impact in the overall prediction. And therefore, what they did was to just prune away these 99.5% weights, leading to a model which is very, very small, just 3 GB in size. Okay. So that's how basically they were able to train a pretty small model. Now, interestingly, this particular model hardly loses on accuracy. So if you compare it, if you here are comparisons on 4 different data sets on 3 different metrics: NDCG at 1, NDCG at 3, and NDCG at 5. Okay. The black line is essentially DiSMEC, and what you observe is that the black line is almost as close to the yellow line. Yellow line is basically a one versus rest framework, 870 GB model. That's basically called as the SLEEC model. So that's that. So now, if you observe in most of these cases, the black line is actually very close to the yellow line. Sometimes it is, in fact, better than the yellow line. In some cases, basically, well, the yellow line is almost close to the black line, right? So essentially saying, DiSMEC actually gives you much smaller models. In fact, sometimes better models as well. And in most cases, it does not really give you, it gives you at least comparable accuracy compared to other one versus rest classifiers. Compared to FastXML that I covered in the previous video, it basically leads to 15% better results on average across these data sets. Okay. So in summary, in this video, I talked about DiSMEC. Essentially, the problem is that low-rank label embedding methods fail for tail labels in extreme classification datasets. Even tree-based classifiers could have poorer prediction accuracy because they try to sort of trade off this prediction accuracy with the prediction speed. Okay. One versus all classifiers are great. They actually led to the best accuracy in this time period in 2017, but they don't scale. They don't scale in training time as well as in size trivially. And therefore, in this paper, people proposed DiSMEC, which basically involves distributed parallel training using OpenMP and in general distributing the processing across multiple machines. And they also, propose this idea of pruning, which is very popular in general in model compression literature and deep learning, but was not that popular in terms of just doing it for one versus all these log loss kind of classifiers. So that's it for this video. Hope you liked it. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.